Good evening, everyone. This is Yashvi Sheth, TA for the course of Basic Principles and Calculations in Chemical Engineering, taught by Professor Subrato Majumdar from IIT Guwahati. And this is the third live session for that course. So we can start the session now. I will share my screen. So, firstly, I will start with the brief of the uh, lectures that were taught in the third week by Professor. So, starting with the brief of lecture 7. So, in the lecture 7, basically the lecture was started with what a flow sheet or process flow sheet means. So process flow sheet is the sequence of process units connected by process streams. So whatever the units and the unit operations and unit processes that are going on in any industry or any process, that all is highlighted and they all are connected with some arrows that will denote the the direction of the arrow will denote in which direction the process or where the material flows from or where the energy flows from. For example, if you have say for example, this is for raw material uh, processing. So the feed goes in here. So if the raw material processing is to remove some of the volatile components, then there will be some gaseous byproduct. So that will be going out. Some product that will be the raw material for the actual reactor. Okay, now from the reactor it will have product plus byproduct. So it will again go into the separator, and finally there will be byproduct and product. Suppose the reaction occurs at very high temperature. So if you provide some sort of heating, then this will be the direction of the water that you are or steam that you are passing. So this represents the flow of energy in and flow of energy out. So this entire block or process flow diagram, so here you can use some specific symbol also. For example, reactor you can show like this. Any specific design or symbol that is used for any specific uh, instrument or the equipment, that also you can use in the process flow diagram. So all the arrows, they are showing the direction of the flow of any material or energy. So this is how the process flow sheet is represented. Now next is general material balance equation. Just a second. Um, so material balance, for getting material balance, say for example you have a system. So let's say that this is the inlet and this is the outlet. Okay, and there is some sort of reaction going on. A gives product B. So now what material balance is, and there is some volume in which the amount A and B are getting stored. So how do you write a material balance? So material balance can be written in the form like whatever is going in and depends on whatever going out, and there will be some accumulation. Okay, Say for example, we are writing material balance for A. So the accumulation, so what happens with A is there is some A going in to the system. This is system. Some A going out of the system. Some A is getting reacted, and there is some A getting stored here. So when you write a material balance, all the streams that are going in or that are being formed into the system, they have species going inside the system or generated, since it will add in the amount of that material in the system, that will be denoted with positive sign, and the species going out of the system, or if it is consumed, then always it will be negative. So if I write for A, then the amount of accumulation or the amount that is left in the system, accumulation in system, will be equal to whatever is coming in, so that will be positive. Okay, inlet of A. Now there will be reaction of A going to B. Now A gives B, which means A is getting consumed in the system. Now consumption is always negative, so consumption of A. Now since there is no generation of A, there will be the amount that is generated is 0 plus 0 minus whatever A which is present in the outlet of A. So this is how we write for this particular case. Now if you want to write it in general, then there will be accumulation of any material, or you can write overall also, accumulation equals to inside the system for any species, there can be inlet of species plus whatever is generated, because generation is always positive. Then there can be consumption, so that is negative because it is getting removed, or and at the last minus outlet of species. So this is the general mass balance equation that you can write. And here here what it is written: accumulation within the system is input to the system minus output plus generation and consumption within the system. Now this involves a chemical reaction. Okay, now if we want to apply this equation when there is no chemical reaction, then it will be a special case. Now since there is no chemical reaction, the generation term in this equation and the consumption term in this equation will go to 0, because there is no generation of that species due to the reaction in the system, and there is no consumption of that species in the reaction in the system due to the reaction. So both these terms will get 0, and that is why the equation will end up into accumulation equals to input to the system minus output from the system. So now next comes is what kind of balances that can happen is, one is material balance, in which we can write it for the species or the compounds or even for atom. Another is energy balance. So similar to material balance, energy can also be written in terms of accumulation of energy Now, how is energy accumulated? Energy accumulation is the energy which is used by the material of the system to change its temperature, so that is represented by mCp delta T, where Cp is the amount of heat, like it is the heat capacity of that material. So it represents how much amount of energy is stored or how much amount of energy is consumed per unit mass of that material to raise the temperature by 1 degree Celsius. So this is the amount of energy which is stored. Just a minute. Okay, now accumulation of energy equals to input of energy in any form minus output of energy plus the generation of energy. Now how can the energy be generated in the system? This can be done if the reaction occurring is exothermic. If the reaction occurring is endothermic, then in that case there will be some amount of energy that is consumed. So this is what energy balance looks like. Consumption of energy in the system. Another terminology that was mentioned in the lecture was process specification. So this is how we relate different process variables to each other, because these are all interrelated. Now there can be also equations where we for example, Raoult's law. Raoult's law is nothing but y, the mole fraction y into total pressure equals to yi p equals to xi pi saturation pressure. So this is nothing but it relates the mole fraction in gaseous state and in liquid state. So it all depends on the system. We can have various laws which will give one equation to be solved. Okay, so this is how we solve all the equations in any system. We will have a number of equations from material balance, from energy balance, and from process, like energy balance is totally different, but from material balance, from process specification, and where we relate various process variables, and from various laws also we can have certain type of equations. Also we can have certain constraints. Say for example, the mole fraction in any system can the total of mole fraction like x1 plus x2 up to xn, it cannot be greater than 1. It is always equals to 1. The mole fraction of all these species is always equals to 1. So this is also a constraint. So where we are bound to do follow certain thing, it comes under constraint. Now coming to the next part, as I mentioned, there can we have to solve mass balance to get various equations and find out the value of how much product is formed and what is the amount of product formed, what in how much quantity. For example, two products are formed A and B, then in how much, what is the ratio of product formed. So all that, or maybe even just unit operation is performed, as you can see here. Then also applying material balance, we can find out how the inlet streams are splitted into two. So for example, there can be two types of mass balance. One is overall mass balance. So what does overall mass balance mean? So say for example, you have this system. Now in this system, without getting into the concern of what are the species present, you just consider what is the total amount getting inside inside the process or inside the system, and what is the total amount of material which is leaving the system. So for applying overall mass balance or material balance here in this system, we have total inlet in the form of, there is one stream P, so that stream is P plus another stream is Q, so Q. There is another stream getting in R plus S. Okay. Now there can be now there can be certain accumulation also. So whatever amount that is going out is W, V, U and T. Now there can be some accumulation, so accumulation term will come here. Now if the process is at steady state, then accumulation is what? Accumulation will be nothing but change in the that variable. Okay, suppose we are dealing with the flow amount of material, that is P, like any concentration C per unit time, then this change will be 0. Okay, so accumulation will be 0 for steady state, and accumulation term will just appear when there is unsteady state, say for example batch process, and for continuous this term will tend to 0. So for steady state we can even say that whatever is going into the system is coming out of the system. Okay, input equals to output. Now if we want to apply component wise mass balance, so here what components do we have? It is in the form of number, and 1 2 3 up to 8. Okay, I guess. And yeah, and y, what does y mean? Y is the mole fraction. Okay, so y1 y2 up to y8, this is nothing but the mole fraction. Say for example, if I want to write the mass balance for component 1, okay, so what I will do is, for steady state process, whatever amount of y that is going into the system, and I will equate it to the amount of y1, amount of one component which is coming out of the system. So if we look into this process, the first component, one number component, is present in P, it is present in Q, it is present in W, it is present in T. Okay, so 4 streams has component 1. So how can we write? So amount of component 1 in P stream will be mole fraction of that component in that stream into the total amount of material which is going in. Okay, now here it is for input. Now in Q, so amount in Q, y1 into Q, this will be like this, because the mole fractions can be different in different streams, equals to now output, because since W is output, so W into y1 in W plus there will be T y1 T. Now similarly, if I want to write it for, say for example, 4 number of fourth component. Now fourth component is present in inlet at Q, yeah, just Q. So for inlet of fourth number of component, there will be just y4 in Q into Q equals to, now where it is coming out in V, and yeah, just in V, so it will be V into y4 V. So this is how we write for component wise mass balance. So similarly we can write for another components as well. Now coming to the brief of lecture 8, here in the earlier lecture what was mentioned is just one system or one process unit, how to apply material balance for a single process unit. Okay, now there can be as I have shown here, there can be n number of processes going on So if I want to write the material balance for that continuous process, then in that case how to write material balance, so that is highlighted in the lecture 8. Okay, so just 1 minute. So now if you have, say for example, this all are certain processes A, B, represented by A, B and C. So let's say the feed that is going into A is F. Now FA, this is FB, this is FC, and this is product P. So now what will you do in this case? This is nothing but series of processes. So for applying balance, you can first consider this process. Okay, so now you know FA, and from that, whatever is, there will be some process parameters and process conditions that you will already know, or you might even know what kind of output quality is required based on the purity of product you want. So based on that, you will apply the balance over here, and you will find out FB or any other parameter that you need to find. Now again you need FB, you know FB, then you can apply the balance in the subsequent systems. So if you have series of such systems which are not interconnected, then what you can just do, you can consider one single system or process unit at a time, solve that process unit and use the data that you have obtained from one process unit for the calculations in subsequent process units. Now moving forward, it is not necessary that all the process units are not interconnected. There can be cases where the processes are interconnected. So first of the such cases, recycle. Now in the continuous industrial operation, what we find out is, say for example, this is reactor. Now it is not always necessary that the reaction goes to completion. The reaction that actually occurs in the reactor, it is quite, the conversion is quite low in the reactor. Okay, so if I give you an example for ammonia process, then the conversion of N2 and H2 to ammonia in a continuous reactor, it is just 70%. Okay, so if you consider just 17%, 1717, so if you consider just this much percentage of conversion, and like this is an approximate value. Okay, now if you consider just this much conversion, then and if we do not recover or reuse the reagents, or we separate the reagents, then there are chances that the reagents are wasted. Or so what we need to do is, we need to recover unused reagents and use it back into the reactor, original first reactor. So what we do, we always add some fresh feed. This is fresh feed. Okay, we give some fresh feed. So this is the reactor where the actual reaction will occur and product is formed. Now as I said, the conversion is actually very low. So what we do is, we separate this product into unused reactant and the actual product. So now we recover that this is, so this will nothing but be the separator of this system. So we recover the product and we recycle, or we send the recovered unused reactant to the original reactor. Actually what we do is, we mix the fresh feed and the recycled stream that contains this unused reactant. We mix that stream, and mixed stream passes through the actual reactor. So there are two terminologies. So this type of case is recycle, where we send the unused material to the feed stream. We mix both the streams and we send it to the reactor again. So here there can be two terminologies. Actually, I will talk about it later. I guess it is coming in the subsequent slides. Next comes is bypass. So what occurs in bypass? Suppose you are sending the fresh feed here to the reactor. So you take out some amount of the fresh feed and you just bypass, or you do this stream, it does not pass through the actual process unit, and it directly mixes with the, say for example, this is the product stream which is coming out after processing. So here we mix P and B to give product. So such processes or such type of operation is required in certain cases. One of the example is the industries that prepare fruit juices. Okay, so it is usually observed that if I want if I have some fruit juice and it is not concentrated, and if I want to concentrate, now this is, so in that case this process unit will be evaporator, because I want to remove water and concentrate that juice. Now what is observed is, if I concentrate in an evaporator, there are chances that the taste of that juice, it changes a bit due to the external or forced evaporation, or due to some any other reason. So what we do, we remove some part of the original diluted juice, we concentrate here, and then we mix it here, both the concentrated and the original fresh juice. So in that case what we do, we are trying to maintain the taste of that juice. So this is one of the example where we observe bypass. So there can be many more systems where we observe bypass. Now next comes is purge system. So purge system is nothing but, say for example you have feed. Now there are chances that feed always is not pure. There can be some amount of inerts or unwanted or material which is not reacting in the reactor. So for this system it is nothing but inert. Okay, so now this inerts also go into the reactor. Now as I mentioned earlier, to recover the unreacted reactants, we do recycle of that unused reactants. So since we separate just the product, uh, so this will nothing but be the phase separator, because it is separated by the difference in the states like gas, liquid, or soap, liquid, solid, etc. So unused reactants are sent back to the reactor. Now unused reactants, along with it there is inert also, which is as it is. So what will happen is, if I like feed stream will have constant and some uniform concentration of inert. Now if I always, there will be some amount of inert always coming in with the feed and always coming in with the recycle. So what will happen is, every time there will be a buildup of inert in the process, and this is actually not required. It will change the process parameters. It can, like if I keep on adding the inert, there are chances that the concentration dilution occurs, or temperature effect is observed, pressure changes. So since this values changes, the operating condition changes and the actual equilibrium will shift, so which is very undesirable. So what we do, is we take out every time when we recycle, we constantly take out some amount of unused reactant, the mix plus inert, so that it is not built up in the reactor. So that recovery or that removal of inert and some amount of unused reactant is nothing but called as purge. um, Purge in that, sorry, purge in that system. So purge is, why do we apply purge, is to remove an accumulation or avoid the accumulation of inerts or unwanted material in, or that might otherwise build up in the recycle stream. So next is makeup stream. So sometimes makeup stream is to avoid, there can be losses due to leaks and carryover. So due to the losses that has been observed, we try to add that much amount of material from outside which is equivalent to the amount that is lost. So one such example that I can give you is the cooling tower example. So what happens in a cooling tower, what we do actually is we spray water from top, and it is like the air flows and air will come into the contact with water and it will cool down the water. Okay, so now as I cool down the water, there can be some amount of evaporation loss, or there can be certain amount of water which is even carried away with air. So now what will happen is, if that much amount of water is carried out, then the if such process continues and there will be a continuous evaporation and carry away of water, what will happen, this water will have certain amount of salts in it. Now as the concentration of salt increases due to the water amount going down, since water decreases, so salt per water will increase, and this will result into scaling being observed, because salts has limited amount of solubility in water. So after certain amount of concentration of salt, it will start scaling up, scaling, and it will eventually affect the efficiency of cooling tower. So to avoid this, what we do is we add makeup water, so that the concentration of salt is always maintained in the cooling tower and scaling is avoided. Okay, so this is the example of makeup. Now coming to the brief of lecture 9. The important definitions highlighted in this lecture are as follows. First is the limiting reagent. Now what does limiting reagent mean? Say for example, if you have A plus 2B gives C plus D, such type of reaction going on. Now in this case, what will happen, it is not like here if I say this is 1, if it is not mentioned, then 1 mole of A reacts with 2 moles of B to give 1 mole C and 1 mole D. Now what does 1, 2, 1 and 1 represent here? They are also called as stoichiometric coefficient. So now for any process or for any reaction to happen, we can give the reactants to the reactor either in stoichiometric unit. Say for example, here the stoichiometry that is followed for the reactants is 1:2 2 for A is to B. So always there is not possible to add 1 is to 2 or for this case or the stoichiometric amount of reagents. There can be some more depending on the process variables. One reactant can be more or another reactant can be less. So for example, if I add, let's say for this system, if I add 10 moles of A and 30 moles of B. So now if I check for the stoichiometry, stoichiometry is nothing but A is to B is 1 is to 2. So if for 1 mole of A to give product, I need 2 moles of B. Now here I have 10 moles of A. So for 10 moles of B, I require 20 moles of B. And for 30 moles of B, I require 15 moles of A. So for this system, I can say that this is the excess reagent which is fed to the reactor, and here feeding 10 moles of A and 30 moles of B. For every mole of A getting consumed, this there will be 10 moles of B left. So A will be consumed first. So this will be the limiting reagent, and this is the reagent in excess. So limiting reagent is nothing but the reagent which is expected to deplete or consume first in the reaction if it is proceeded or if it is allowed to go to completion. So completion is a mandatory term here. Now there are few definitions, so that has to be looked upon. So those definitions are conversion of system. So conversion is nothing but moles reacted per moles fed. If you want to find it in percentage, then it multiplied by with 100. So for conversion, it is suggested that we measure the conversion for limiting reagent. Okay. Otherwise, there can be conversion of both A or B, whether it is limiting or not. But for systems, it is usually preferred to measure in for limiting reagent. Now conversion can be overall and single pass conversion also. So if you have a system, if okay, so in this system there is recycle. Okay, so there will be some amount of reagent unused will be recycled to the system. So there can be overall conversion or there can be single pass conversion. So now what does overall conversion mean? Say for example, it is reaction is nothing but A gives B. Now you are feeding A and it is pure. So overall conversion is nothing but you don't see this R stream and you check for what amount of A I am letting it in and what is the amount of A which is coming out. Say for example, what you are giving 100 moles of A in the feed and it has 5 moles here. So what does this mean? The conversion is nothing but what is the amount disappeared, it will be amount that is reacted. Okay, you can consider that ways. So amount disappeared will be 95 divided by what is fed is 100 into 100. So this is nothing but 95% conversion. So this is overall conversion. Now if you want to find out single pass conversion, so wait, I will write a common definition. Overall conversion is P minus, oh, sorry, F minus P upon F into 100. Okay. Now if I want to write for single pass, what we do, we just take into consideration this much system. So whatever is going in and whatever is going out, you consider just this much, okay, and measure what is the conversion. So single pass conversion is nothing but M minus X upon M into 100. Next definition is this is for the selectivity. So selectivity is for the reactions where we have two types of products. Say for example, A gives B gives C. It can be of this type also. This is nothing but series reaction. Or it can be of type A gives B and A also gives C. Now here it can be such that if this is desired, this is undesired. Here it is desired. Here this is undesired. So what does selectivity mean? It is the moles of desired product formed to mole of undesired product formed. So we always want this selectivity to be high because always it is required that moles of desired product is always larger than what is undesired. So we try to optimize with this selectivity. So now next the term was extent of reaction. So extent of reaction is nothing but how much reaction is proceeded, okay, which is represented by this equation. So if I want to find the moles of any reactant or product, then this is the amount of initial moles of that species plus, now here Vij is nothing but the stoichiometric coefficient and epsilon is the extent of reaction. Okay, so for product this will always be positive, so number of moles will increase, and for reactant this will be negative, so the amount of moles will decrease, right? Now coming to the next lecture, which is also talking about the reaction, which is here some special type of reactions are discussed, which is combustion reaction. So what does combustion mean? It is nothing burning or oxidation of fuel to release energy, because combustion is an exothermic process. So for any reaction to occur, there will be some amount of energy released. So any fuel usually has carbon, hydrogen, sulfur in it. So all this gets converted into its oxide form. Now combustion can be of two types. If I have limited supply of oxygen, because oxygen is the only one which oxidizes or which results into combustion. So oxidation is due to oxygen, okay. So combustion can be complete combustion or it can be partial combustion as well. So if complete combustion occurs, then C reacts with oxygen to give CO. Actually you need to balance, right now I am not balancing. So this will be for partial combustion because oxygen is limited. What does partial combustion mean? Oxygen is limited. And if I want complete combustion, then it will give me CO2. Now there are certain terminologies for combustion, because what does combustion mean? We add externally oxygen. It can be pure also, it can be added in the form of air, because air is free. So and purifying air to give oxygen. And how do we derive pure oxygen? By purifying it. So which is cost taking process. So what we do, we usually take air to for the combustion. So theoretical oxygen demand is nothing but the moles of oxygen required for the complete combustion of fuel. So what we do is, so for example, if you need to do the combustion of methane, so CH4 plus O2 gives CO2 plus H2O. Now if you balance the reaction, H is 4, carbon is 1, so this will be 2, and C is 1, so the 2 plus 2, so this will be 2. So theoretically I need 2 moles of oxygen for complete combustion of 1 mole of methane. So this is what theoretical oxygen demand mean, which is moles of oxygen required for complete combustion of fuel. Now as I mentioned, we usually take air instead of pure oxygen, which contains usually N2O2. N2 is in 79 mole percent, rest is you can take 21 mole percent, because there are certain other materials also, other species also, which are in trace, so we neglect that. So usually you take this. Okay, so we fed air instead of pure oxygen. And for theoretical amount of oxygen, whatever we get the quantity of air, that will be nothing but theoretical air demand. Now since the process is exothermic, we usually give air in excess. Okay, so what does excess oxygen or excess air mean? It is nothing but the amount of air or oxygen that is fed over and above to the theoretically required oxygen or air. So for that, how do you calculate percentage excess air? It is nothing but excess of air per unit theoretically required air into 100. Now what does excess air mean? Excess of oxygen per unit theoretical oxygen into 100. Now these two are same, because the conversion of oxygen to air moles, it is just by a factor, which is 21%. So this actually it will be same. Now how do you calculate the excess? Excess is nothing but O2 entering minus O2 which is actually theoretically required, divided by O2 required. This will be into 100. Right? Now moving to the assignment. The first question is, for a steady state process without chemical reaction, a general material balance equation is what? So a general material balance equation is nothing but accumulation equals to input minus output plus generation minus consumption. Okay, so there are two key terms here. The process is steady state. So what does steady state mean? Accumulation will be 0. Okay, and there will be no reaction. It is without reaction. So there will be no generation term, there will be no consumption term, as I have already explained in the starting of the lecture. So what does this mean? This will be 0, this will be 0. What is left is input equals to output. So for steady state process without chemical reaction, material balance ends up into input equals to output. Next comes is the significance of the purge stream in a chemical process is to do what? Now, if we look into the options, the meaning of purge stream is I have already mentioned in the lecture, in the earlier part of lecture. So purge stream is nothing but we take out some portion of recycle stream and that is withdrawn from the system. So why do we withdraw? That is the question. To remove accumulation of unwanted inerts or material from system, to add material to increase conversion, to add inerts to increase the temperature of the system, or remove product to increase the separation. Now all these options are incorrect. What does actual purge stream mean? We do not want any unwanted inerts to accumulate, so this is the correct option. Now next is, a material balance can be written in terms of, it can be written in terms of mass, moles for a species, for atoms also. So if we look into the options, total overall mass or moles, this will be nothing but each compound balance. This is nothing but overall, and this is not like this is overall, and this is nothing but component wise mass balance, as I have explained earlier. Or there can be an atomic mass balance also. So all the options are correct in this case. Next question is, a distillation column is used to separate a binary mixture of benzene and toluene. Different streams of feed and distillate and bottom product and mole fraction of benzene in other streams are shown in the figure. For a given system, overall mass balance can be expressed as. So what do you want to do is find out the overall mass balance. Now overall mass balance, what you take into consideration? You just take into consideration the streams without like what is the total amount of material which is going in, total material input, and you relate it equals to, here since distillation is a continuous process, accumulation will be 0. At steady state we can have input equals to output. Total material input should be equals to total material at output. Now what is the total material input? It is represented in the form of F. So F equals to, what is coming out? D and B. D plus B. So the correct option here is F equals to D plus B, B option. Moving forward to the next question. Sum of the mole fractions of component is dash. So let's take a system where we have components 1, 2, 3, 4 up to n, and their mole fraction is represented by xi. It can be x1, x2, x3 up to xn. So if I write the mole summation of mole fraction, summation of xi from I equals to 1 to n, what will be that? X1 plus, now this will be the number of moles. So if I want to convert into mole fraction, what will be done? What will be the mole fraction? It will be nothing but x1 by x1 plus x2, which is mole of that component divided by total number of moles. So this is moles, okay, sorry, moles of component. And if I want to take summation of mole fraction, so x1 by total number of moles plus x2 by x1 plus x2 plus up to xn plus dash dash dash, it will be up to xn, mole fraction of each and every term. Now since the denominator of each is constant, summation of mole fraction would turn out into x1 plus x2 plus up to xn, and it will be nothing but x1 plus x2 plus x3 plus dot 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 till xn. So this since both numerator and denominator are constant, it will cancel out and it will end up into 1. So what does this mean? Summation of mole fraction of all components equals to 1. So which is the correct answer? This. Next question is, different flow streams are shown in the figure. Recycle stream from the given diagram is dash. So what does recycle stream means? Recycle stream means we take out some amount of unreacted reactants and some amount of product and we send it to the original process. So which stream is being sent out of the is taken out of the product stream and it is sent back? It is F. So F here is the correct answer. Now next question is, output and consumption are two negative contributions in this to the system. So this is the true statement because whatever we are taking out or whatever is consumed, they are taken negative because they are decreasing the amount of that material in the system. So we take that as negative. Next question is, the feed of 100 kilomole containing 45% of benzene is fed to a distillation column. So let's draw a plus. So there is one suggestion: if you want to solve any material balance, it is better to, based on the question, if there is no flow sheet or flow sheet given or system given, then it is better you draw that system. Okay, so first we will draw that system. So we have one distillation unit. So this is feed stream F, which is containing 100 kilomole per hour. Okay, total flow rate, and 45 mole percent is benzene. So 45 mole percent is nothing but mole fraction of benzene in feed stream. So let's say mole fraction of B represented as XB, which is nothing but 0.45. There will be a distillate stream. Okay, so now that distillate stream is containing 95% of benzene. So XD you can say as 95% or it can be 0.95. And bottom, let's say it is W and it contains XW is nothing but 0.1, which is 10%. You need to calculate the amount of distillate. So for that, what we will do, first we will write two types of balances. One is overall and one is component. Okay, so let's write first overall. Overall will be what? Whatever is going into the system and whatever is going out. So F equals to D plus W. Now F is what? 100 equals to D we want to find out and W also we need to find out. Let's say this is equation number 1. Now writing the component balance for benzene, whatever the amount of benzene that is going into the system is, a certain amount is present in feed stream. Okay, so what is that amount? XB into F equals to whatever amount it is present in distillate, which is nothing but XD into D, and what is the mole fraction in W, so XW into W. So if I put up the values, what will be it? XB is 0.45 into F is 100. XD is given as 0.95 into D plus XW is given as 0.1 into W, we don't know. So let's say this is equation number 2. Now if I solve this two equations, equation 1 and 2, if I solve those two equations, I will multiply this equation by 0.1 because I need to find out distillate and I will eliminate W. So I will multiply first equation by, let's say, minus 0.1. So what will come as minus 10 equals to minus 0.1 D. plus, like it will be minus 0.1 W, and this will be 45 equals to 0.95 D plus 0.1 W. This will cancel out, and what will left is 0.85 D equals to 35. So D is coming out as 41.17 kilomole per hour, because the unit will be same as F. Next question is match the following. Actually, the options here mentioned in this question are wrong. So based on the definition, we will find out our own options. So PERT stream is what? We avoid the non-reactant components to build up, and we build up by maintaining it below the permissible limit. So where is such option? It is number 3, the entire stream or a part of stream uh, which is coming out of the processing zone due to the buildup of non-reacting components beyond the permissible limit. So PERT stream is 3. Bypass is what? Certain part of reactant that does not undergo any processing. So it is and joins the product stream. So it is of shown in number 2. Unsteady state is what? The parameters change with time. Example is batch process. It is number 4. And recycle is nothing but we send some amount of unreacted stream to the original processing unit, which is 1. So there is no match in these options. So please correct this question. Next is the reaction A gives 2B plus C takes place in a reactor. Refer this figure. Now the reactor effluent is sent into the separator, and the overall conversion of A is 95%. So what does overall conversion mean? Let's say this stream is represented by P. Okay, sorry, this is not required actually. This is product P stream. It has A, B and C. Let's say this stream is X. This is R. So now what we are given is we have overall conversion of 95%. Now what does that mean? Whatever is going out, inside, which is in the form of pure A, 95% is consumed in this area, and only 5% is going out. So what does that signify? Let's take a basis here. So for solving any such questions, we take a basis. So let's say, and how do we take a basis? Based on what we are given in the question. So analyze the question and decide. Since we are given the overall, so the basis should be such that we should be able to find out certain value. Okay. So here we are given overall conversion of A. Now overall conversion involves feed F and this stream. So it is better to take this as basis. So let's say basis is feed is nothing but 100 mole per hour, or you can take 100 moles also. For continuous process, it is better to write it in the form of flow rate. Now since feed is 100 moles per hour, and since it is pure, entire is A. Now 95% is converted. So what does that mean? 95 equals to whatever the amount is present in P stream and whatever is fed. So since 95 is converted, A in feed minus A in P divided by A in feed. So this is 100. Okay, so 90 into 100. 95 equals to 100 minus A in P upon 100 into 100. This gets cancelled out. A in P equals to 5 mole per hour. Okay. So this what we found out, A in product stream. Now the product stream from the separator consists of B, C and 0.5% of A which is entering the separator. So now we know this, and which is nothing but 0.5%. So this is nothing but 0.5% of A which is present here. So let's say A here present is XA. So XA which is present in X stream, it is nothing but 0.5%. So 0.5 by 100, don't just take 0.5, it is percentage. So 0.5 by 100 into so 0.5 by 100 into XA should be equals to 5, because 0.5% of this is 5. Okay, so if I solve it, what will be the answer? 5 by 0.5 into 100, it will give me 1000 moles per hour. So this is the amount of A in X stream which is going into the separator. Okay, just a second. We'll take another slide. So now moving forward, what do we need to find out? We need to find out what is the percentage conversion in the reactor, which means single pass conversion. So we need certain more data. Okay, now while the recycle stream consists of remainder of unreacted A, so what does that mean? Remainder of A means recycle contains. Now if we apply material balance for component A here, what is the balance of A here? Inlet is nothing but 1000 equals to A in P stream plus A in R stream. So this we know. So R is nothing but 1000 minus R. Sorry, A in P, which is nothing but 5. So it comes out to be 995 mole per hour, which is the amount of A present in stream R. Okay. So based on this data, this much data is sufficient for calculation of the single pass conversion. So I can simplify for you. 100 moles of A goes into the reactor, as feed stream. This is mix, this is reactor, this is X, this is separator, this is product, and this is recycle. So recycle has 995 mole per hour of A. This has 1000 mole per hour of A, and this has 5 mole per hour of A. So this is the simplified form. To find out the conversion in reactor R, what we need is, we need moles going into the reactor and moles going out of the reactor. So this moles going out of the reactor we know, and moles which is going into the reactor, which is in M stream, is nothing but M equals to A in F plus A in R, which is 100 plus 995, which is equals to 1095 moles per hour. So M contains 1095 moles per hour of A. So single pass conversion or conversion of reactor is nothing but 1095, which is mole fed into the reactor minus moles coming out of the reactor, divided by moles fed into 100. Sorry. So this will come out to be 8 point approximately 67, which is the answer. Moving forward for the next question, limiting reagent for a complete reaction is defined as what? So it is nothing but as I have explained in the lecture earlier, It is nothing but the reagent that gets depleted first, not last, not least, or which is remaining as residue. It is also false. So it is the first depleted reagent. Now next comes is the assume a reaction A plus B gives C. The yield of C is the ratio of what? So yield is what? Moles of product formed divided by moles of reactant reacted. Here everything is in terms of C and A. So we will find yield in terms of A and C. So yield of C is nothing but mole of product formed. What is the product formed for C? Mole of C in output divided by mole, just a minute. Sorry to disturb you. Which is nothing but moles of A reacted. So the correct option here is moles of A C in the output and mole of A reacted. Option A. Next question is extent of reaction at the start of reaction is what? So what does extent of reaction mean? Extent of reaction is amount of reaction completed or how much reaction is proceeded. So at start of reaction, what does that mean? This is the key word here. Start of reaction means T equals to 0, whatever may be the unit, second, minute, etc. So at T equals to 0, there is nothing reacted. Okay, so extent of reaction is nothing but 0. Next question is, the stoichiometric coefficient will be treated as positive for reactant and negative for product. So stoichiometric coefficient, what we do, suppose example we have A plus B gives C plus D. So stoichiometric coefficient for each and every one is 1, 1, 1. So what we do, stoichiometric coefficient has some sign, positive and negative. Now positive is generally used for one which is produced or product, and negative is used for consumed. So this is nothing but it is related to the mass balance. You can relate it with that also, which is consumed reactant. So this is a contradictory statement, so it is false. Next question is, for an elementary reaction A plus B gives C plus D, 1 gram mole of A and 1 gram mole of B reacted to give C and D at equilibrium. At reaction temperature T, equilibrium reaction constant is 1. Calculate the mole fraction of A at equilibrium. So how do we write equilibrium constant K? It is nothing but concentration of C raised to the power of its stoichiometric coefficient, which is nothing but 1 for each and every case. Concentration of D divided by concentration of A into concentration of B. So now since this is 1, concentration of A into concentration of B equals to concentration of C into concentration of D. So for balancing the equation at equilibrium, what we will do, now let's write initial moles 1, 1, 0, 0. Now let's say X is the amount of moles which is consumed at equilibrium. So consumed will be X, X, 0, 0. Formed will be what? 0, 0, X, X. Since the stoichiometric coefficient is 1 in each and every case, it will be similar amount of consumption and similar amount of production. So what is the amount left? It is 1 minus X, 1 minus X. This will be X, this will be X. So this can nothing but be related as the concentration. So if we put up these values, it will be 1 minus x into 1 minus x equals to x into x. So what is left here? 1 minus x square, 1 minus 2x plus x square equals to x square. Now x square gets cancelled, and 2x equals to 1, so x is nothing but 0.5. So this is the amount of moles which is remaining, moles of A. So x is amount of in gram mole left at equilibrium. Now this is in gram mole, and you need to find out mole fraction. Okay, so for that what you need to do is find out the total moles at equilibrium. Now total moles will be what? Okay, total is summation of all the moles which is left at equilibrium. So 1 minus x plus 1 minus x plus x plus x. So x gets cancelled out. It is nothing but 2. Okay. So anyway you can say that, because since the stoichiometry is maintained, so whatever is going in, it will be coming out at equilibrium. So 2 is going in, 2 will be formed. So if you want to find out mole fraction of A at equilibrium, it is nothing but moles of A that is left at equilibrium, divided by total mole at equilibrium, which is nothing but 0.5 by 2, which is 0.25. Okay, so correct answer is 0.25. Next question is, for an elementary reaction 2A plus 3B gives C plus 2D, 1 gram mole of A, 2 gram mole of B fed initially in the reactor, and 2 gram mole of C and 1 gram mole of D is obtained at equilibrium. Vi is the stoichiometric number of ith species in the reactor. What is the value of Vb? So since it is just it just wants to find out the stoichiometric coefficient, it does not have any relation with this gram mole which is going in or going out. So stoichiometry is just the coefficient here. Now since it is asking for B, so stoichiometric number is B 3 for B. Now it has sign also. Since B is a reactant, it is consumed, so it will be negative. So the answer here is -3. Next question is, selectivity of a reaction is defined as, I have told you this in the explanation, which is nothing but moles of desired product upon mole of undesired product. So mole of desired product by undesired product is option A. Okay. Next question comes out to be, for a given parallel reaction, what is the conversion? Okay, here you have been given desired and undesired product just to divert you, just to distract you. Conversion of any reactant does not relate what is desired, what is undesired. It is just related what is the amount reacted and what is the related to the amount reacted and what is the amount fed. So conversion. So here the reaction will be, instead of single reaction, A will be consumed in both the reactions. So conversion here will be nothing but moles of A reacted in both reaction per unit mole of A fed. So which is nothing but option C, mole of A reacted, moles of A fed. Coming to the next question, consider a reaction CO plus 2H2 gives CH3OH. What is the stoichiometric ratio of H2 to CO? Now stoichiometric coefficient Vi of, like V for CO, is nothing but -1. For H2 it is -2. Now if I want to find out the ratio for H2 to CO, it will be -2 by -1, which is nothing but 2. Answer here is 2. Coming to the next question, consider a reaction CO plus 2H2 gives CH3OH. Calculate the kilomoles of CH3OH produced per kilomole of CO reacted. So for that, what we will do is CO reacts with 2H2 gives CH3OH. What does the reaction mean? 1 mole or of CO reacts with 2 mole H2 to form 1 mole CH3OH. So 1 mole gives 1 mole of CH3, 1 mole of CO gives 1 mole of CH3OH. So if I have 1 kilomole of CO, it will give me 1 kilomole of CH3OH. So what we are asked is per kilomole of CO reacted. So which means 1 kilomole CO is reacted. So how much amount of CH3OH will be formed? It is nothing but 1 kilomole. Okay, so it is 1 kilomole. Answer is 1. So trick in this question can be the reaction is per 1 kilomole. You can be asked what is the amount of moles of CH3OH formed. So you need to convert this 1 kilomole to moles unit. So which 1 kilo means 1000 moles. So what will be the amount formed? 1000 moles. So this can be a trick, or this type of twists also can be seen in the question. So yeah, that's it from my side today. Thank you everyone. Thank you for this session. I will end this meeting and end this session now. I will stop sharing my screen. Thank you everyone.